Welcome to example number 5. This question involves an EMF that is due to a time-varying magnetic field. So we have a magnetic field that you can see here shown pointing out of the screen towards you that is passing through this stationary loop of wire with this resistor. And as the field changes over time, as shown by the graph over here, it's increasing, then it's stable here, and then it's decreasing, we'll find that an EMF will be generated during certain time intervals. So in part A, we're asked to plot the graph of the EMF in the circuit as a function of time and label the axes quantitatively with numbers and units. Okay, so the first thing we'll need to understand here is that according to Faraday's law, the EMF that is generated by Faraday's law of electromagnetic induction is caused by a change in magnetic flux over time. So as long as the flux is changing, then we have an EMF that is being generated. And if you recall, the magnetic flux is equal to BA times cosine of theta. So now, if we were to determine the general equation, I guess, for the EMF induced, so let's start off here with part A. The EMF is equal to negative N times the change in flux over the change in time, where the change in flux is equal to BA cos theta. Let's plug that into here. Negative change of BA cos theta all over the change in time. And then if we were to, I suppose, rewrite this, take out the things that are common in our equation. We know that the B field is changing over time, so that is not going to be pulled out. But the area of the loop, I assume that is remaining constant. So we could pull out the area out of the equation. And I also assume that the angle that the B field is penetrating out with respect to the plane of the loop is also constant as well. So those two things we could pull out. Negative N times A times the cosine of the angle. And then we have really a change of B all over the change in time. Now this is really, if you look at this graph, this is really the slope of the graph. Okay, you could rewrite this if you wish as negative NA cosine theta, and then B, say, final minus B initial at some time, divided by the time final minus the time initial. Okay, so let's go ahead and calculate it for different time intervals. So for t equals 0 to 2 seconds, our EMF will be equal to, and we'll just start substituting in here. Now N, what's N in here? How many turns of wire do we have? Oh, it's just one turn, so that's just really one. Then we have the area of the loop. We have a radius, and this is a circle, so we could use pi r squared. The radius is 0.5 meters squared. And then multiplied by the final B field at 2 seconds, which is 5 teslas, minus the initial field, which is 0 teslas, all over the time, which is basically 2 seconds minus 0 seconds. And that gets us an answer of negative 1.96 volts for 0 to 2 seconds. So let's carry on. That's part 1, I guess, of A. Let's do part 2, which would be for the next interval, which would be from t equals 2 seconds to 4 seconds. And if we look at this, notice from the graph here, the B field is not changing. So I could substitute in here negative 1 and then pi and 0.5 squared. But what you're going to find is that you're going to have 5 teslas minus 5 teslas all over, say, 4 seconds minus 2 seconds, and your answer is going to be 0. There's no potential because there's not going to be any changing field, and none other quantities are changing over time. So we don't have any EMF generated during that interval. Okay, moving on to 3 now. So we have from 4 seconds to 8 seconds, and our EMF would be negative 1 times pi times 0.5 squared. And then we have the final field is 0 Teslas minus the initial field is 5 Teslas all over 8 seconds minus 4 seconds. And that will give us an answer of positive 0.982 volts. So from 0 to 2 seconds, we had an EMF of negative 1.96 volts. For t equals 2 to 4 seconds, no EMF. And for t equals 4 to 8 seconds, we have a positive EMF of 9.82 volts. So now we can go ahead and construct our graph. And there we go. I've created a graph here scaled with up to 1 volt and negative 2 volts over here. Now for the 0 to 2 seconds, you have to realize that immediately at 0 seconds until right up to 2 seconds, it's a constant voltage of negative 1.96 volts. It's not a changing voltage, it's constant. So it's going to be a constant negative amount. So right around here, I would say, about there, you have that constant amount of negative 1.96 volts. And this is occurring for 0 to 2 seconds. So actually, I just realized this is actually a little bit too long here, because this is really 2 seconds, 4 seconds, 6 seconds, and 8 seconds. And right at 2 seconds, then suddenly from 2 to 4, we don't have any potential. So I'm going to draw a horizontal line right at 0 to 2 seconds here. Or I should say 2 to 4 seconds. Now, you might be wondering what's happening in here, because it suddenly is right at 2 seconds, it goes from being at negative 1.96 volts to 0 volts. So usually in here, we either draw nothing or draw a dash line. Otherwise, it wouldn't be a function. So sometimes people will just put a dash line in there. And then afterwards, from 4 seconds to 8 seconds, you're going to have a constant potential of about 1 volt, 0.982 volts. And that's the graph for part A. Okay, now moving on to part B, we're asked to plot the current through the resistor R and label the axis quantitatively, indicate the arrows on the sketch and the direction of the current through the resistor R during each time interval. Okay, if we were to ask to find the magnitude of the current, you already know the voltage, and hopefully you're thinking, oh, all I really need to do is apply Ohm's law to get part B. I'm just going to do that over here, part B. The Ohm's law says that the voltage is equal to the current times the resistance, so therefore the current will be simply the voltage divided by the resistance. So if I was looking for t equals 0 to 2 seconds, our current would be that voltage divided by the resistance. The voltage is negative 1.96 volts divided by our resistance. And our resistance is up here, must be indicated somewhere. Oh, there it is, at 20 ohms. So moving down here, let's go ahead and insert that into our equation. So we had 20 ohms, and that gave us a current of negative 0.098 amps for the 0 to 2 seconds. And then as we continue on here for t equals 2 to 4 seconds, the current will be the EMF over the resistance, but the EMF is 0, so therefore the current will also be 0. And for t equals 4 seconds to 8 seconds, the current will be that EMF of 0.982 volts divided by 20 ohms, and that gets us a current of 0.049 amps. Notice this is negative and this is positive, indicating those two currents are in opposite directions. So for t equals 0 to 2 seconds, we had a current of 0.098 amps. From t equals 2 to 4, we have 0 current. And from 4 to 8 seconds, we have a positive current of 0.49 amps. And the graph I've shown over here is basically the same as the other graph. The only difference now is that the values on the y-axis have changed. So we just instead have from 0 to 2 seconds, we'll have a current of negative 0.98 amps, 0 current from 2 to 4 amps, and then 4 to 8 amps, we have 0.05 amps, roughly speaking. Let's go back to our top of the diagram. And here I just want to qualitatively look through and talk about the direction of the current as it is shown in the diagram. So over here we're indicating as going counterclockwise as being positive in our diagram. And we just want to make sure when is it actually, when it's 0 to 2 seconds, is it a clockwise or counterclockwise current? We obviously know 2 to 4 seconds there's no current, but 4 to 8, is that clockwise or counterclockwise? We have to establish that. So what I normally do is I draw sort of two pictures. I have a before picture. I'll just assume this first picture I'm provided is the before picture. And over here I've shown an after picture that shows a situation at, say, at t equals 2 seconds, and over here we'll say this is t equals 0, or maybe 1 second, because at 0 seconds there's no field. So let's just say at 1 second it's here, and at 2 seconds you can see that the field has gotten stronger, so therefore I've drawn them a lot more compact and closer together. Now, the flux has increased, and because there's an increase in flux that is coming out of the screen towards you, we're going to be having to create field lines. The loop will provide its own field lines that counteract this change by basically canceling out these extra field lines that are going into the plane of the loop here, and so that we end up with the same amount of dots that we have here. So we have looks like 9 dots, and I have back to 9 dots again in the picture. So using the right hand rule, where your thumb points in towards the screen, your fingers will curl in this direction, which is the clockwise direction. So our current here is clockwise. So that the current that we found from 0 to 2 seconds, we have a clockwise current. And then when you go from 4 to 8, you're doing the reverse, because your flux is decreasing, so it reestablishes those field lines in the original direction of the field. And so therefore this current here will be counterclockwise. So we go down to our graph here. The beginning current here at the bottom here, the negative current that we're finding here at the beginning from 0 to 2 seconds, that current is clockwise. And then this current that is positive, that current over here is counterclockwise. And you can see actually from the diagram above, we've indicated going counterclockwise as being a positive current, and then clockwise would be the negative current. Okay, a last part in this problem is to determine the rate of thermal energy production in the resistor. And so hopefully you're thinking here, rate of thermal energy production. A lot of people don't quite remember that. Well, it's energy, and it's a rate of energy. That's power. So let's go ahead and calculate the power. There's a lot of ways you could do part C. So actually, and I'm just realizing I don't have any room here. Let me just add another page here. Okay, to determine the power, I'm just going to scroll down to my next page here. Our power is determined by a couple equations. You could use the current times the voltage. You could use the current squared times the resistance, or you could use the EMF squared divided by the resistance. Any of those equations will work. So we just need to go through each of the time intervals and determine the power. So from 0 to 2 seconds, we can use the current we just got. I squared times R. We have a current of negative 0.098 amps squared times the resistance of 20 ohms. That'll give me a power of 0.19 watts. And then if we continue on, we have for t equals 2 to 4 seconds, the power is I squared times R, but remember the current is 0, so there's no power for that time interval. And then from 4 seconds to 8 seconds, power is I squared times R, and our current in the last interval of time is 0.049 amps squared times the resistance of 20 ohms. And we get a power of 0.048 watts. Okay, so then we can go ahead and plot our graph now. And so in this case, our power is all positive. As you can see here with a graph of just showing a y-axis that's all positive here. From t equals 0 to 2 seconds, we have a power of 0.19 watt. So I'm going to draw a horizontal line right about here till 2 seconds. Then it drops right down at 2 seconds, so that t equals 2 to 4 seconds, we have no power. So I'm just going to draw a horizontal line in here. And lastly, from 4 to 8 seconds, we have a power of 0.05 watts approximately. So I'm going to draw a horizontal line right about here. You should notice that all the powers are constant over this time interval. By the way, interesting enough, if you take the area under this curve, you'll get the energy. Remember that power is equal to energy or work over time, so if you multiply the power by the time, which is the area under the curve, you're going to get the energy that is being used up during those intervals. And that's it for this example.